Some engineers are trying to measure a flagpole, and it's kind of a pain because the tape keeps falling off when they try to climb up, and they're trying to measure the height of the flagpole, and then a mathematician comes along and says, "Oh, what are you guys trying to do?" And they say, the engineers say, "Oh, we're trying to measure the height of this flagpole." So the mathematician takes down the flagpole and then pulls it out of the ground and then measures it with the tape and then tells them, gives the measurement and then goes away. And the engineers sort of talk to each other and say, "That's typical of mathematicians. We wanted the height and he gave us the length." Okay, so not so good. Okay, so let's see. Is this working? Okay, so this is a hackathon. You guys should do this. Maybe you guys can be the next Mark or Susie Zuckerberg and make a lot of money. Okay? So we're going to review the depth first search in directed graphs, and we're going to go through some other stuff. We're going to talk about directed acyclic graphs. And we're going to talk about this concept called topologically sort and strongly connected components. Okay? Okay, so remember what directed graphs are. So directed graphs, so you're given a graph G equals VE. So let me just introduce a little bit more notation, or a little bit more terminology, just to, sometimes the language can help us get a better picture. So E is a subset of V cross V. It's just pairs of nodes. That's all that notation means. So an edge UV, the way you think of it is an edge from U to V. Okay? When we write UV, it's from U to V because it's a directed graph. Okay? The tail is U, the head is V. Okay, so this is an example. The edge here is AB, it's from A to B, the tail is A, and the head is B. Okay, so there's just terminology there. And now we showed you how to do direct depth first search on directed graphs. So what we got out of that was these depth first search trees. Okay, so now these trees, especially with directed graphs, you have sort of more specific things going on. So the root is the starting point of a tree. It's where you start and explore, right? And V is an ancestor of U, means that V is on the path from U to the root. Okay, so you have V is a descendant of U, that's vice versa, and it's just sort of a natural thing. Okay, so depth first search on a directed graph, just to recall. We're just running this algorithm, so we start at a node U and then we start exploring. Those are the pre-order numbers that are appearing. Those red edges are the tree edges. So right now, with this part of the tree, you can say that A is the root. D is an ancestor of C. It's actually the parent of C. C is a descendant of D. C is a descendant of B. C is a descendant of A. Okay? And now these little numbers that are appearing are just the pre and post order numbers that we saw before. So when you first visit a node, you start a clock. You start the clock at 0, and you start at A. There's the clock at 0. There's a clock at 1. You write down the pre-order as soon as you come in. There's a clock at 2, at 3, and then you pop off. Then you explore this blue edge. You see that you've seen it before, and then you go backwards 5, 4, 5. And then you go all the way back to B, and you go to the next arc coming out of B. And then 6, that's the post-order number is 7. The post-order number is 8. There, the pre-order number is 9. The pre-order number is 10. The clock ticks. You go look at this edge. It's a cross edge. You've already seen D. So on. Post-order, post-order, post-order. Okay? So these are the tree edges here are the red edges. So they're forward edges, and they have this particular property for the post-order and the pre-order. And the property is that this interval of V is the pre-order comma post-order. So it says the interval, let's look at an example. Let's look at AF. So that's a forward edge. So the interval is 10, 11 for F, right? The pre-order is 10, the post-order is 11. And for A, it's 0, it should be 13. I still didn't fix this. Okay, 0 to 13. And then it's 0. So another way to view these intervals is you can say, well, if I can, this interval is inside of this interval. I mean, this interval is inside of this interval, so I could stick it in here. That's how the book does it. Okay? So a back edge is this blue edge here. And there, the interval of V, the interval of the tail, contains the interval of the head. Because the tail is an ancestor. V is an ancestor of U, right? Here in this case, B is an ancestor of C. So since it's an ancestor, it was on the stack the whole time before when C was explored. So therefore, C's time on the stack, which is what these post and pre is inside the time interval in which B is on the stack. Okay? So this is really about loving the stack. Okay, these pre and post are really just talking about how the stack is behaving. Okay, so and this is the example 3, 4 is the interval for C, which is the tail. So the interval for the tail is in the interval for the head for the back edges. Okay, and the cross edges, their intervals are disjoint. The interval of V is completely before the interval of U. Okay. So that's what these cross edges are. It's a node you've already explored, but it's not on the stack. It's not one of your ancestors. Okay, so either you've already explored it and it's one of your ancestors, in which case it's a back edge, or you've already explored it and it's not on the stack anymore. So its interval is already completely disjoint. Okay, so that's what a cross edge is. Those are the only kinds of edges that are possible in the relationships with these intervals. Okay, so now the directed acyclic graphs are, what are directed acyclic graphs? So again, an edge is, okay, well actually instead of talking about directed, let's just go over this one more time. A tree edge is a direct call. If you just think about depth first search as a algorithm, the tree edge is just tree edge U to V is one where explore is called on V from U. That's what a tree edge is. It's your child. It's a direct, it's really, the tree edge is your call tree of these explorers. Okay, your forward edges are, you're going, you called V and then you call W, and there's an edge that pops from U all the way to W. That's a forward edge to one of your descendants. A back edge is an edge to an ancestor. A cross edge is none of the above. Again, for a cross edge UV, V is already explored. That's why you don't explore it. If you explored it, it would be a tree edge. Since you did not explore it, it must already have been explored, in which case it must either be a back edge, but that would be an edge to an ancestor, which we would say is a different object, or it is what's left. It's the cross edge. Okay, so now a directed acyclic graph. Okay, so it's basically a directed graph without cycles. Okay? So why do we care about directed graphs? Okay, so goodbye. Hello. Okay, that's clearly I screwed up, right? I mean, I'm not socially very adept, but I should have said hello and then goodbye, right? It's very important to do it in that order, right? Hello, and then goodbye. It's very important to go this way and not that, because otherwise people just think you're strange, right? So this is a very compelling example of why you want it. Okay, well, it's not so compelling. So maybe you have a dependency graph here. So this is telling you what needs to happen before something else happens. Okay, so processing this graph would be interesting. Now, one thing, if somebody gives you a dependency graph and it has a cycle in it, is that kind of indicative of a problem? Yeah, so dependency graphs shouldn't have cycles. So you would think these things are everywhere, these dependency graphs, these directed acyclic graphs that don't have cycles. I mean, directed graphs that don't have cycles. they should really be everywhere, right? Okay, so the first thing we want to do when somebody gives us such a dependency graph maybe is we want to say, well, is it really even a dependency graph? Does it have a cycle? Okay, so that's one problem. So let's look at an example. So now the question we want to know is this acyclic? Is this graph acyclic? What do you think? Is it acyclic? Right. It's not acyclic because, right? There's a cycle, right? So this would be not a valid acyclic graph. Okay? So that was easy, right? Because we saw it. But now if it looks like this, it's a little harder to tell. A little noisier to see where the cycle is, right? Obviously, I just added edges, so that old cycle is still there, but it sort of stood out before because there weren't very many edges. So it's actually kind of a computational problem to even figure out whether the thing has a cycle or not, right? It could be very dense. Deleting one edge, it could be a very dense graph and still have no cycles. Okay? Yeah. Hello? Was there a question? Okay. Okay, so is this an acyclic graph? And the answer is no, but how do we tell? So we're obviously going to tell using depth first search. So again, we have our depth first search thing with all our fancy labels. So what do you see? We remember where the cycle was, right? It's from B to D to C. Okay? So the tree edges won't create a cycle, right? Because you won't ever cross the tree edge. And you won't make this edge from C to B a tree edge because you've already seen B. The whole notion of a cycle is you explore, you only explore things you haven't explored before. So the tree edges don't form a cycle. But this blue edge, what kind of edge is this blue edge? It's a back edge, right? So the blue edge is a back edge. So if your depth first search tree search actually has a back edge, then you must have a cycle, right? Is that clear? So this is a back edge. Again, one way to check if it's a back edge is, we have this notion that it's an edge to an ancestor. That's sort of a conceptual notion, but you need a computer notion, which is, here's something very specific that we've computed, these numbers, and checking whether 3, 4 is inside of 1, 8 is all you need to do to check for whether something's a back edge, right? It's a very local operation to check whether something's a back edge. Okay? So now if you have a back edge, you have an edge. Now we think of our conceptual notion of the back edge, which is it's an edge to an ancestor. So if you have an edge to an ancestor, you have tree edges from your ancestor. So this edge goes from U to V, and V is an ancestor of U in the tree. And you have tree edges from V to U. That's what it means for V to be your ancestor. So that means you have a cycle. You have a path from V to U and an edge from U to V. So that creates the cycle. So the presence of a back edge means you have a cycle. Okay? So there's one way to check if you have a cycle in your graph. You do depth first search, and you check if there's a back edge. Okay, so am I done? Do I know that every graph with a cycle the depth first search has a back edge? I know if I have a back edge in depth first search, I have a cycle. That's what I've argued. Okay, what else do I need to argue to say this is an algorithm for figuring out whether something has a cycle or not? Right. So so the back edge means there's a cycle. It means if you find a back edge, it's not acyclic. But what if it is cyclic? You need to show that there must be a back edge to have a full algorithm. Okay, so a graph has a cycle if and only if there's a back edge. So back edge implies cycle. That's what we just argued, right? If there's a back edge, you have an edge back to an ancestor. Since there's a path from the ancestor to you and an edge back to the ancestor, that's a cycle. Okay? So now we want to say if there is a cycle, that implies the existence of a back edge. Okay? So let's think this is the cycle. Let's assume there is a cycle. So we have a cycle from V0 to V1 to some number of intermediate vertices and back to V0. Okay. So now let's think about now this is where we really, you have to think a little bit here. You have to really concentrate. The explore Think about what the explorer does. So what we're going to do is we're going to say at some point it discovers a node on the cycle. Right? There must be a first point where it discovers a node in the cycle. Right? So let's just assume the node it discovers is V0. Okay. This is without loss of generality because we could rewrite the names of the cycle so that whatever the first node it is discovered is named V0, right? We can shift this representation around. Okay? So we're assuming that explore in DFS, the first node on which explorer is called on this cycle is V0. Okay? So what happens when we explore it? When explorer V0 returns, all the nodes on the cycle must be explored. Right? Is that clear? Because when you call explorer on a node, remember we said when you call explorer on a node, it reaches all the nodes. The properties of DFS is that it reaches every node that is reachable from this node. Okay? So it will, before explorer V0 returns, V1 must be explored, and V2 must be explored, and V3 must be explored, and V4 and V5, all the way up to VK. Okay, so if these were all explored and done, you were done exploring them, you had to be done because you called them recursively, right? You have a recursive call to explore, you have a call to explore V0, and at some point during that call, you call explorer in V1. At some point during that call, you call explorer V2. And you never finish the explorer V0 until explorer V2 returns, right? So that says for every one of these VIs, the interval that they're on the stack is inside the interval of V0. Okay? So in particular, the interval of VK, the last node on the cycle, is inside the interval of V0. Well, when this interval is inside of this interval, that means it's a back edge. Okay? So we found a back edge. It says, given a cycle, the algorithm will output an edge that is a back edge. Okay? Okay, so so cycle implies back edge. So back edge implies cycle. That's easy because you just show the cycle. But this is a little bit more subtle. You have to think about how the algorithm is. We're trying to say the algorithm behaves in a certain way if there's a cycle. It actually will indicate that one edge at least is a back edge. And the way it indicates a back edge is the pre and post order numbers. And those pre and post order numbers for VK will be inside the interval for V0. And that's just what the definition of a back edge is. Okay? So we went from this sort of, there's some path through a tree, and then I jump back to that one, which could have a lot of nodes in the middle of the path, to checking a very local condition. For this edge, all you need to do is check this very local condition. There's 4 numbers here. You check them. Oh, yeah, this is a back edge. There must be a cycle. Okay? Okay. So how do you check if something is a DAG? Any ideas? What? What? Repeat again? I can't hear you. I'm sorry. Say it again. Okay. Say it again. Yeah, I'm just asking, how do you check? So we have this theorem. How do you check? I want to figure out an algorithm for checking if it's acyclic now. Okay? So that's what I'm going to check. So I use this fact. A graph has a cycle if and only if there is a back edge. So I'm going to run DFS, and that's fast, right? Order V plus E. And I just check if it's a back edge for every edge. And how much time does it take for each edge to check whether it's a back edge? Well, there's 2 intervals. You have the pre and post number for U and the pre and post number for V. So checking that whether one is inside the other is trivial. So it's order E time. So it's an order V plus E time algorithm for checking if the graph is acyclic. Right? Okay, so it's a really fast algorithm for checking whether the graph is acyclic. So that's good, right? DFS is doing more and more for us. It's telling us how to do connected components. It's telling us how to check if something is acyclic. So what I could say now is this hello to goodbye graph doesn't have cycles. And I can do that really fast. I could probably do that really fast before. But I could also say this graph doesn't have cycles. And I can do that really fast. But is that really what you want to do? Okay, it doesn't have cycles. What do you really want to do with this dependency graph here? You want to have yeah, there's no cycles. You can tell in linear time. So is that really interesting? It's not really interesting, right? It's by itself. What you really want to do is you want to find an ordering for your build. You want to say, okay, I'm going to do this task first, and this task second, and this task third, right? Yeah, you can try that. Where things are cool. What does it mean to be cool? It means every arc goes from an earlier vertex to a later one. Okay? So the topical. So this brings about this problem, which is the real problem you have with DAGs. This is what you really want. If somebody gives you a DAG, what you want to do is you want to find an ordering where each edge goes from an earlier vertex to a later vertex. You don't have anything that you haven't built yet that you depend on. Okay? So this is the topological order problem. So again, let's look at an example here. So a linear ordering looks like that. So every arc here goes from left to right. Okay, let's just check the arcs. The one from A to E is fine. Any one from A is going to be fine, right? Because it's first. So let's look at F. The outgoing arc goes to D, which is afterwards. What about C? C has no outgoing arc, so it's fine. E to F, that's the outgoing arc there. B has a G, and B to D. So all the arcs go this way, right? Okay, so this is a valid linear ordering for them. Okay, so one thing to notice is does depth first search, and I drew up the numbers for depth first search. Does it tell you how to do this ordering? Okay, is there some pattern here? Yeah, what's the pattern? That's one thing. He did say, he said he's using the tree. He's suggesting to use the tree. If anybody who's a descendant of A must be after A. So that's true. But that's a little bit of a conceptual thing, yeah. Right. So that's both a more complicated conceptual thing and a really simple algorithm. What he said is, let's look at the post number order of A. What is it? It's 13, right? It's the largest one there. Okay? When is A popped off the stack? It's popped off last, right? That's what post order number means. It's popped off. A in this case is popped off very last, and it's first here, right? And E, when is it popped off? Second to last, right? And so on. F is popped off third to last. B is popped off fourth to last, and so on. Okay? So what this says is that every edge, so let's see what the property is that we're using. So what it says, this algorithm we're suggesting is that, well, just do your depth first search, and output in reverse post order number. And that will be a topological sort. Okay? Okay, so now why would that topologically sort the graph? Why would it make sure that every edge goes in the right direction? Well, what we want is for every edge in the DAG UV, we want the order to have the property that U comes before V, right? That's what topological order means. It means that you have I should have maybe given a path here. So you have some order of the graph, and for any edge, U, B, U should come before V. Okay? That's what a topological sort means. Now there might be other edges and so on, but U needs to be before V in the topological order. So this property says that post of U, for every edge in a DAG, post of U is greater than post of V. So if we output it in an order where the bigger U's are before the smaller, the bigger post order number is always before the smaller post order number, we get a topological sort. Okay, so if you do an inverse post order number, it will be topologically sorted. For every edge, for all UV, the order of U will be less than the order of V, right, if we do it in inverse post order. Okay? Okay, so, wow. Okay, so let's prove this property. Well, first of all, there's no back edges, so let's look at the other kinds of edges. Okay, the tree and forward edges. In the tree and forward edges, again, the interval of the tail contains the interval of the head. Okay, because it's going to a descendant in the call tree. So the time I'm on the stack is always going to be longer and bigger than anybody I call, even recursively. So that's what the forward edge is. So the interval of U contains the interval of V, which means if you write out all the numbers associated with the interval, is the pre of U is before the pre of V, which is always before the post of V, which is before the post of U. So these last two says the post of U is greater than the post of V. Right? So for tree and forward edges, this property holds. So, and now there's cross edges. For cross edges, remember the whole interval of U was after the whole interval of V. So clearly the post of U is after the post of V. So this property holds. There's no back edges. So the topological sort algorithm is the output in post order number, in reverse post order number. Yeah. It doesn't matter. Yeah, you may not explore the whole tree, but you keep exploring, right? DFS explores even if you don't explore the whole thing. Just in post order number. You sort them in post order number. Right? So this is a proof that works, right? It doesn't matter. It's just for DFS. This is true for any DFS for any ordering. He's asking a question. There's a subtlety here. You have this graph. So the sort of the obvious depth for search would start here. So the obvious depth for search would start here, and you would get a tree of this form. After the first explore, if you explore this, you get this to be. This is just a graph. It's just a picture right now. Okay, so it's not a tree at all. Okay, so and then you go to B, and then you go to D, and you go to C. That's sort of what you think the depth first search is going to do. And you can say the post order number here is, let's just do it. So the pre is 0, the pre is 1, the pre is 2, the post is 3, the post is 4, the post is 5. Did I do it wrong? Oh yeah, I'm not finished. Okay, sorry. Okay. The pre for this is 5, 6. That's why I put them in slides. Okay. So this is 7. Okay, so there, now if you do it in inverse post order number, you're fine, right? You get A. Which one's next? Now all the arcs go in the right direction. You got an arc from A to B, an arc from C to D, an arc from B to D, and an arc from A to C. See, the arcs go from left to right. Okay? But this was, I picked the order. I picked where to start the Explorer here. But the depth first search should work no matter which order I start the thing. Okay? So I could start the depth first. It is true by convention in this class when we draw examples, we usually start with A. Okay? But that's not, depth first search doesn't care. It could start in whatever order it wants. There's no order here. So let's say I start the depth first search by first exploring C. Okay, so then what I get is a different kind of graph. I get C to D as a tree edge. And then I get A to B as this is a cross edge. Right, I'll call it a cross edge. A to B, okay, as a tree edge. And then I get A to C as a cross edge. And a B to D as a cross edge. Okay? Okay, so those are very different looking things, right? This depth first search is very sort of different looking than this depth first search. Either one should work for topological sort. Right? I didn't say anything about the ordering of the graph. Okay, otherwise you can't, okay? But the proof doesn't either, so it's fine. So both of these work. But what does the proof say I can do is if I output in inverse post-order number, everything's fine. So let's look at the post-order number here. So this is 0, 1, 2, 3. This is, what is this, 4, 5, 6, 7. Okay? So now let's output an inverse post-order number. What is it? It's A. What's the next one? B. What's the next one? C. What's the next one? D. Okay, so now is this a valid ordering? So we have an edge from A to B, A to C, B to D, and C to D. Okay, every edge goes from left to right, from earlier to later. So it's all valid. Okay, it's a different ordering, in fact, from this one, right? It is actually, but they're both valid topological sorts. Okay, so now this but where you start gives you very different trees and very different sets of back edges and forward edges and stuff. But it doesn't matter. It just doesn't matter. Okay, so okay, is that clear? The algorithm works in whatever order you do explore. Okay, okay, so. Okay, so the runtime is you're just doing a depth first search and then outputting in reverse post order. So yeah.
So in that example, you went to C to D, and then you realized that you hadn't explored everything, so you just picked A and you went again, right?
Yeah.
So, but most problems let you not know what all the points are, and you figure them out as you go.
Oh no, that's not our model here. Our model is the following. Our model is we have a graph, and we have a graph data structure. Where are you? Okay. So our model is we have the whole graph explicitly. So we have a list of nodes. So we explore from one node. Okay. Remember this? Here's the DFS algorithm. So DFS of G is right? So we assume we have a list of all the graphs at the beginning, all the nodes. So this in this example, this will be A, B, C, D. That's the one way that's the one order we were given these vertices. But there's no particular reason to think we were given these vertices in that order. In the other one, it was C, A, C, B, D. So this one, we're assuming the order in which we went through these nodes is C, A, B, D. In this one, in this case, it's A, B, C, D. Okay? So if you're thinking about a world like the web, where you're doing depth first search, where you can only follow links, you're right, but that's not what we're talking about. We're given the dependency graph explicitly. Okay? Okay, so any other questions? Okay, so there's some subtlety here. Sometimes it's a really good question because it sort of exposes that this works for no matter what, right? It's very minimal, the expectation on what you're asked, what you're provided. Okay? So basically the procedure, okay, so the one question is, we're sorting here, right? And at some point we said sorting takes n log n. And here I'm claiming this running time is order v plus c. So there's an exercise here. How do you actually output them in reverse post-order number? So how would you output them in reverse post-order number? Okay, well, this is how I learned to love the stack, right? This is what this whole thing is, right? What is a post-order number? It's when I was popped off the stack. Okay? So as soon as I pop myself off the stack, I output it. Okay? So now what that does is the procedure, post-visit, you remember DFS in Explorer, there's this little post-visit. It just outputs. Whenever you pop off the stack, that's when you call this procedure post-visit, right before you do it. So you output yourself when you got popped off the stack. Okay? So what that does is it gives you the thing in post-order number. Now you have the list in post-order number. Now if something's in post-order number and you want it to be in reverse post-order number, then you just reverse it, right? So you can actually output the stuff in reverse post-order number because you love the stack, right? You love the call tree stack. So we don't need to sort at all. Okay, so it's really linear time. Okay? Okay, so now let's talk about a little bit more about DAGs because we really love DAGs. There's another sort of obvious thing in a directed acyclic graph is if there's a source is defined as a node with no incoming arcs. Now, is it clear that a node should have no incoming arcs in a DAG? Right. Because otherwise, here's a proof that there must be some node with no. Let's prove a different thing. Okay, so I don't know. I'm going to get confused. This way is easier for me to think about. Okay, so there's a sink as a node with no outgoing arcs. Okay. Now, is it clear? Oh, let's try this again. Is it clear that every DAG has a node with no outgoing arcs? Yeah. Okay. Same answer. Good. Okay. Why? Is there a simple proof? Yeah. Right. Okay. So what he said is, after you topologically sort, the first node clearly has no incoming arcs, and the last node has no outgoing arcs. Okay. So now we're using this fancy algorithm that we proved through the sweat of our blood to show this very, very simple thing. But this is actually a much simpler thing. This you can prove in a different way. So how do you show there's no arc? There is a node with no outgoing arcs. Yeah.
Well, if you assume that there wasn't one contributing factor to the directly acyclic graph,
Yeah, that's right. So he said you can construct a cycle if there is. Let's assume yeah, he's saying, assume there's no nodes with no outgoing arc. Every node has an outgoing arc. Okay? If every node has an outgoing arc, what can you do? Well, let's start somewhere. Okay? If I start somewhere, I can always leave. Right? I just want to fit in this joke. It's not the Hotel California. But it's the whole point of this discussion. Okay, so if you're at a node, you can leave, right? Because you have an outgoing arc. Okay, and so you go to that node. And what can you do from there? Leave. What can you do from there? Leave. And at some point, you're going to see the same node again. You only have so many nodes. If you see the same nodes again, if you walk around and you see the same place again, there must be a cycle. Okay? So there must be a node without outgoing arcs. Okay? So these arguments are kind of fun and interesting, and you could go enjoy them with your friends. But this is another way to prove it. The way this gentleman suggested is the highest post-order node is a source because it's first in topological order. Obviously, there's no incoming arcs. Yeah. No. He asked if we ever deal with infinite number of nodes. No, we don't. No. So this argument doesn't work with an infinite number of nodes. So the lowest post-order number is a sink, so it's a node without outgoing arcs. Okay, so every DAG has to have at least one source and one sink. So now here's another topological sorting algorithm, which is you find a source, you output it, you repeat. Okay? So naively, that takes order nm, but it's an exercise to do a better implementation. Okay? So this is a different topological sort algorithm. It's not so much more interesting than DFS because DFS is fast, but we're going to use this concept of source and sink for the next part, which I'll get to after the break. So once you take a break for a minute or two. Okay. 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 So, all right. So, I don't know. Back a long time ago, when I had a kid and I had a wife, and then so me and my wife were talking about having another kid, and so we asked. Well, I actually had two kids. It doesn't work with one kid. Okay. So I had two kids, and they're like 4 and 3 and 5 or something, 3 and 5 maybe. And so, maybe the 3-year-old, I don't know, my kids are not very fast, so the 3-year-old really couldn't talk or anything. This was kind of a lump. And so, so we were discussing having a third kid. And of course, I don't know why we were asking our older kid, well, what do you think about should we have another kid? And should we get another kid? And he said, yeah, this one hits. Oh, sorry. His sister. Okay, should we have another kid? Oh, no, yeah, we should get another one because this one hits. Okay, never mind. Okay, sorry. It's actually funny, but I didn't tell it right. Okay, so you see, he misunderstood the question. He thought we could trade this one in. Okay, all right. Okay, so never mind. Okay. All right. So. Okay, so where am I? Okay, so. Okay, so connectivity. So now we're going to talk about connectivity in directed graphs. So we talked about topological sorting in directed acyclic graphs. Now we want to get order from chaos in any directed graph, okay? So now you have cycles in some places, you don't have cycles in other places. You want to learn a little bit more about the structure of this graph, okay? So one thing is we want to know when two nodes are connected. Now what does it mean for two nodes to be connected? Does it mean that there's a path, two nodes U and V. Is there a path from U to V? Does that mean they're connected? Does that fit your intuition? It's not quite enough, maybe because you could also have, well, there's a path from V to U. Neither of those. So really, what we probably mean is that there's a path from U to V and a path from V to U. That's what it means for nodes to be connected. And we call them strongly connected, okay? So this is sort of the generalization of connected this is the thing you have to do to make this connected definition that works for undirected graphs easily. If there's a path from U to V, there's obviously a path from V to U because the edges are undirected. You can go either way. But in these one-way arcs, for U and V to be connected, you should be able to get from this corner to this corner and back from this corner to that corner, okay? So it's transitive. It has nice properties to define these this way. Because if U is connected to V and V is connected to W, then U is connected to W. Yeah.
Isn't that a cycle though?
Yeah. Yeah. It's not a directed acyclic graph. So we're working on general directed graphs that might have cycles. Okay? Yes. So we want to know something about these graphs, right? We were trying to build some structure on that, right? What's the first thing we wanted to do for undirected graphs? We wanted to find the connected components. We're going to do the same thing here for directed graphs, for directed graphs. Yeah.
It's also symmetric, but is it reflexive?
Yeah. We'll just define it to be reflexive. You're connected to yourself.
So you can make an equivalence relation.
Yeah, you can make an equivalence relation. Yeah. No, that's good. Thank you. Good question. So he asked if it's also reflexive. So a U is connected to itself. I should have put that on the slide. You're right. So if it, okay, so that means it's a relation, and that means you can partition into equivalence class. Because with this definition, U has a path to U. It's just U. Okay, so that's the way we're defining it. Okay? So what we want to do is we want to find these equivalence classes, these subsets of nodes that are all connected to each other. Okay? That's what we want to do. We want to partition the graph into these kinds of objects. And it has a lot of applications, which we won't get to in this lecture. But you'll see it. Okay? Okay, so let's see our example again. Okay, so where's the strongly connected components here? Okay, where's the strongly connected components here? Well, there they are. Okay. So G is connected only to G, right? There's no path from it to anybody and back, right? G is in a component by itself. From B, you can get to C by going through D, and from C, you can get to B. So B is connected to C. B is also connected to D. So B, C, and D are all connected in the same strongly connected component. And A, E, and F are all connected, right? There's a cycle there that contains them all. Okay? So a cycle, for example, every pair of nodes on the cycle are connected and are in the same strongly connected component. So one thing we can do with this this sort of thing, right? With connected components, we could take the connected components. We saw that the graph fell apart, right, for undirected graphs. Okay, here, is there some structure among these strongly connected components? Say we collapse them into single nodes. What would you see? What do you see? What is that? Is that a special kind of directed graph? It's a DAG, right? It's a directed acyclic graph. Once we collapse the nodes in the strongly connected components into one node, then if you collapse the arcs as well, you see arcs only go, from, in sort of a DAG-like manner. Okay? Collapsing strongly connected components yields a DAG, a directed acyclic graph. Okay? Why? Well, if you had a cycle in this graph, then all of those nodes involved in that cycle, you could put them together in one strongly connecting component. Right? Because there'd be a way between any pair of nodes and any of those super nodes that are on that cycle. Okay? So the strongly connected components decomposition is just like a connected components decomposition, except for connected components, when you collapse them, you just get a bunch of disconnected points. Here, you get a bunch of nodes that are interconnected via a DAG. Okay? Okay, so now so basically this is a property. Every directed graph is a DAG of strongly connected components. So how might we find the strongly connected components? Okay, so any ideas on how you might find it? Any ideas at all? Yeah. It would be a piece of one. Yeah. So I think he has something that approximates. Yeah, go ahead. All right. Okay, so those are the two versions. This is what you do when you do algorithms. You're like, well, let's start at A and see if I'm on a cycle. That's what Francois said. And then I forgot your name. Is it Mike? What? Michael. Yeah, Michael. He said, well, you know that any cycle any nodes, all the nodes on our cycle are in the same strongly connected component. So somehow, if you see a cycle, you should do something with it. So maybe you collapse it and start again, right? That's one thing you can do, right? Yeah. What's?
I was going to say, as soon as you see a backend, just collapse the nodes, and then recursively do that, so it keeps collapsing until it's complete.
Right. So he's saying, man, he is a fancy programmer. So he's going to keep track of his stack, and he's going to go along his stack. He's going to say, oh my God, it's a back edge. I know all the nodes on he's actually extending this algorithm to say, well, I have this big stack. I know I have a back edge, so I know all of these nodes are on the stack. So I know where my cycle is. I actually have it with me, right? I have it on this call stack. Okay, so now I piece it back together, and then I do something, and I collapse it, and then I continue my depth first search. Now, this is some fancy programming. Did you know you said that? Sorry, but okay. Okay, so I think that's what he's picturing, really. I mean, he's a programmer. This is what you do. Okay, so this is fine, right? But this is getting ugly, right? It's getting like, oh my God. So let's step back. What was the algorithm for DAGs? Well, you do depth first search, output them in post order. Done. Okay? Wouldn't it be nice if we could do that with the strongly connected components? Okay, so let's look at properties of our DFS. Instead of going in and being super hackers, let's just step back and see what we can get from the properties of these pre and post. Okay, from this introspection we did on this algorithm. So one thing you can do is explore visits all the nodes reachable from you. So if you just run explore on a node in the sync component, what do? Which nodes do you find? All the nodes in the sync component, right? You get all the nodes in the sync component. Okay? So then you output the visited nodes, and then you repeat. Okay. So let's look back here and say, what we could do is it's in a picture. We're working on this picture. We're working on this graph. I mean, in our minds, okay? And we say, well, if we just run explore from G, what do we get? Which nodes do we visit? Well, we only visit the nodes in G. We get all the nodes in G's component. So now what we could do is we could remove G. And now, what's the remaining? If you remove G, what's the sync component of the remaining graph? Well, it's this B, C, D. Now, if you choose a node B and you start an explorer from there, you get B, D, C. And that's it. You don't get anything in here because there's no arcs from B, C, D to A, E, F. So you get all the red nodes. You remove them, and then you start again. So this algorithm says, if you get all the nodes in the sync, you output these visited nodes, and then you repeat. This is exactly what DFS does. It just picks some order in which to explore the nodes. So if we could just have this order be such that the first one is in the first sync component, the second one is in the second sync component, and so on, after removing that, you'd be good. Okay? So this way you can get all the nodes in the sync component. Of course, that begs the question. Yeah. Right. Okay, so there's no sync in the directed graph at all. There might not be. Okay, G, if you take away G, there's no sync in this. Okay, but there's a sync in this DAG. Okay, so what I'm saying is, that's a good question. What I'm saying is take a node in the sync component of this DAG. Okay? Any one of the nodes in the sync component of this DAG. In this DAG, it's not a very good example because it's only one. But say we threw out G, there would be two components in this DAG, and there would be B, C, and D. And there's many nodes in the sync component. None of those nodes are syncs. So it's a good question, really good question. So it's a node in the sync component. Any node in the sync component. Again, there's no syncs, and there may be no syncs in the graph. But there's definitely nodes in the sync component. Okay, so you output the visited nodes. The question is, how do you find a node in the sync component? It's easy to find a sync in a regular directed acyclic graph. You just look at all the nodes and look at one without any outgoing arcs. There are no syncs in this graph, maybe. Okay? So the node, again, we're going to use our post orders. So the node in the highest post order number is in a source component. Okay? So we're going to use this property. So let's put aside this. Forget this. Just forget it for a moment. Okay, put it on the stack. Okay? We're going to explore this slide. Okay? That's on the stack. Okay? So the node with the highest post order number is in a, it wasn't really meant to be a joke. It was really meant, that's what you should do. Just put it aside for a minute. Okay? So the node with the highest post order number is in a source component. Let's just think about this. Let's think about depth first search. Okay, what does depth first search do? How do we love a stack? Right? It says the last person off the stack is in a source component. Okay? That's what it says, is in a source component. It's sort of the analogous thing to the DAG. The last one off the stack in a DAG is the first, is a source. But this one, we're proving this other property. Okay? So let's see if we could prove this property. Now it's a little bit more complicated because there's no node that's a source. We're just saying it's one of these larger set of objects. Yeah. Not necessarily, not in this example, right? So in this example, the first node you checked was C, and the last one off the stack was A. Right? And that was important, right? It was because we put it on the stack later. Okay, so the stack consist of many calls to explore the top levels. Okay? So what he asks is, isn't the first one you explored, isn't that the last one off the stack? It is for that call to explore. But DFS has this loop. It also does this over all vertices. So the last explorer called from this loop is the last one. Okay? Okay, so now we're going to do a more complicated property. If now we're going to think about two components in this strongly connected component graph, and say this component C and C prime are strongly connected components with an edge from C to C prime. The highest post-order number in, okay, this one is kind of hard to parse. So let's look at it again so you get another chance to parse it. Okay, and then let's look at a picture so we can parse it with the picture, okay? So what it says is that if C, let's think of these two components, A, E, F, and B, C, D. Okay, those are two components. Let's think of C as AEF and C prime as BCD. Okay? So there's an arc from some node in AEF to some node in BCD. That's what the property says. It looks like this. It's there's an arc this to this. There's two components and there's an arc from it. Okay? That's what C and C prime are. And what it says is that it talks about post orders, so let's write down the post orders. This is a post order traversal of this graph. Okay? So I'm rewriting them down with the post orders here. Okay, I'm replacing the nodes with their post orders. Okay, what it's, because the property is talking about post order number, highest post order number. Okay, so now what it says is there is a node in here whose post order number is higher than any node in there. That's what this property says. So that's true. 14 is clearly higher than 9, 4, and 5. Okay? We could also apply this lemma to the red and the green. We could take the red to be C and the green to be C prime. Okay, what it says is that there is a node in the red set with post order higher than any node in the green. So that says, now the post order number, the 9 comes from this B over here. So the post order of B is larger than the post order of G. So 9 is greater than 8. So we have the condition. What the condition does not say is that every node in the red set has higher post order than every node in the green set. Right? That's not even true. Right? Post of C is not higher than post of G. So this property says something, but it's a little bit subtle to parse. It says there is a node in predecessor strongly connected components with a higher post order number than me. Okay? So the highest post order number in C is bigger than any post order number in C prime. It does not say every node in C has higher post order number than every node in C prime. That's not what it says. Okay? Okay, so let's prove it. If a node U is in C, U in C prime is explored first. So either again, we got to think about properties of our algorithm. Our algorithm is depth first search. Okay? So in depth first search, we keep calling explorer on things. At some point, we explore a node in either C or C prime. So let's assume we first explore a node in C prime. Okay? So if we explore a node in C prime, that's the downstream one, right? There's C and C prime, which is upstream and downstream, right? So you have C and C prime. So let's say the first one we explore here is here. If we explore here, we explore all of this, right? And then we pop off the stack. And then after that, at some point later in time, a node in here is explored. So clearly there's going to be every node in here is going to be explored, is going to be popped off the stack after every node in here. Okay? So there clearly is somebody with a post order number here that's bigger than every node in there, because every node in there is explored first and popped off the stack. You cannot reach, when you do an explorer down here, you don't reach this. Why? Because there's no cycles in this strongly connected component graph. Okay? So that's what that says. So explore U gets to all of C prime and none of C. So every node in C is explored after every node in C prime. So therefore, there's a node in C with a higher post-order number. If, on the other hand, you do this, you explore a node here first. Now what happens is you might explore some of these and pop off, but eventually, before you call explore of U, when does explore of U return? It can't return until it explores all of this, and all of these explores return. Okay? So it says the post-order number of U is higher than the post-order number of all of these, because these are explored recursively by this call. Okay? So their post-order number, or when they return, the post-orders, they return before explore of U call. Okay? So that's all of C and C prime will be explored before returning from explore U. So U has a higher post-order number than any node in C prime, and in fact any node in C. Okay? That's the proof. So this proof says the highest post-order number is in some source component, right? Because it says, you know, because it's just inductive that therefore, if one component has an arc to another component, it has a higher post-order number. So the source component has no incoming arcs. It only has outgoing arcs. So it must have the highest post-order number. Okay? Okay, the highest post-order number is in some source component. There might be more than one. Okay, so the algorithm is run. Remember, now I'm just reiterating the old algorithm we said. We run explore on the node in the sync component, and we output the visitor nodes and repeat. And now we found a way to find the sync component, or did we? What's the problem here? I gave you an algorithm to find the node in the source component, but this algorithm before is my algorithm for strongly connected components was to run the explorer on the sync components. Okay, so what do I do? Any ideas? What? He said the lowest post order. No, that doesn't work. Yeah. Okay. Right? You just reverse the edges in the graph, right? So if you reverse all the edges, what used to be the source component is now the sync component in that new graph. Right? GR, we're going to call it GR. The source component in GR is the sync component in G. So now the algorithm is run DFS on GR, the reversed graph, to compute the post-order number. The highest post-order number V in GR is in the source of GR, and therefore is in the sync of G. Okay? So you output the nodes visited, then you call explore on V, and then what do? So now you have one of the components. You've output one of the strongly connected components, right? So that's good. I'm pretty happy. So what do I do now? Well, I just loop, right? That's one thing I can do. So I need to find another node in the sync of the unvisited part of G, right? So that that works, but it's kind of slow, actually, because I keep doing the same. What do I do? Then I go and run DFS on G of R without this visited part, and then I do it again. It seems like I keep exploring the same darn graph over and over and over and over again. Okay? So I have to recompute DFS, or can I use this post-order number again? Yeah, I can. Good answer. Okay, so well, let's look. Let's see what I got out of these post-order numbers. Those are the post-order numbers? Those are the post-order numbers. Okay. Okay, so what happens, what am I going to run? What is this algorithm? I'm going to run it on the one with the highest post-order number. What's the highest post-order number? 14. 14, I'm going to run it on 14. I'm going to discover this green component. I'm going to remove this green component from the graph. Okay? So now, what am I going to do? Where's the highest remaining post-order number in this graph? Is that a sync component in the remaining graph? Yes. How about now? Well, there's only one component, so it clearly is. What this says is that's not an accident. This property plus plus we proved is we said if C and C prime are strongly connected components with an edge from C to C prime, then the highest post-order number of C is larger than the highest post-order of any node in C prime. So after deleting this sync component, the one with the highest remaining post-order number must be in a sync component. And after deleting that sync component, the one with the highest remaining post-order number must be in a sync component. Okay? Okay, so that's one DFS is enough. So you first, the first explorer of G, you remove the sync component. It removes this, now we have to go back and forth between G and GR, so it's going to spin your head a little bit, or ping pong your head a little bit. Okay? So removing a source component of G removes a sync component of G. That's what we've done. It removes a source component of GR. So the highest remaining post-order number V in GR is in a component with no in edges, right? It's in a source component in GR, which means it's in a source. It has no in edges. That's what this property says. It says if I have the highest post-order number, it's because nobody's ahead of me. If somebody has if there's an arc to me, then that person has the highest post-order number. Okay, so I have no in edges. If I have no in edges, what am I? A source component. Okay, I'm in a source component. Okay, and now it's in GR. I'm in a source component in GR, which means I'm in a sync component in G. Okay, so what's the algorithm? I run DFS in GR. I compute the post-order numbers, and then I just run the undirected connected components algorithm in G in reverse post-order number from step 1. Okay? That's